Uranus, seventh planet in distance from the Sun and the least massive of the solar system's four giant, or Jovian, planets, which also include Jupiter, Saturn, and Neptune. At its brightest, Uranus is just visible to the unaided eye as a blue-green point of light. It is designated by the symbol. Uranus is named for the personification of heaven and the son and husband of Gaea in Greek mythology. It was discovered in 1781 with the aid of a telescope, the first planet to be found that had not been recognized in prehistoric times. Uranus actually had been seen through the telescope several times over the previous century, but dismissed as another star. Its mean distance from the Sun is nearly 2.9 billion kilometers, 1.8 billion miles, more than 19 times as far as is Earth, and it never approaches Earth more closely than about 2.7 billion kilometers. Its relatively low density, only about 1.3 times that of water, and large size, 4 times the radius of Earth, indicate that, like the other giant planets, Uranus is composed primarily of hydrogen, helium, water, and other volatile compounds. Also like its kin, Uranus has no solid surface. Methane in the Uranian atmosphere absorbs the red wavelengths of sunlight, giving the planet its blue-green color. Most of the planets rotate on an axis that is more or less perpendicular to the plane of their respective orbits around the Sun. But Uranus's axis lies almost parallel to its orbital plane, which means that the planet spins nearly on its side, its poles taking turns pointing toward the Sun as the planet travels in its orbit. In addition, the axis of the planet's magnetic field is substantially tipped relative to the rotation axis and offset from the planet's center. Uranus has more than 24 moons, natural satellites, 5 of which are relatively large, and a system of narrow rings. Uranus has been visited by a spacecraft only once, by the U.S. Voyager 2 probe in 1986. Before then, astronomers had known little about the planet, since its distance from Earth makes the study of its visible surface difficult, even with the most powerful telescopes available. Earth-based attempts to measure a property as basic as the planetary rotation period had produced widely differing values, ranging from 24 to 13 hours, until Voyager 2 finally established a 17.24-hour rotation period for the Uranian interior. Since Voyager's encounter, advances in Earth-based observational technology have added to knowledge of the Uranian system. At Uranus's distance from the Sun, the planet takes slightly more than 84 Earth years, essentially an entire human lifespan, to complete one orbit. The eccentricity of its orbit is low, that is, its orbit deviates little from a perfect circle, and the inclination of the orbit to the ecliptic, the plane of Earth's orbit and nearly the plane of the solar system in general, is less than 1 degree. Low orbital eccentricity and inclination are characteristic of the planets of the solar system, with the notable exceptions of Mercury and Pluto. Scientists believe that collisions and gaseous drag removed energy from the orbits while the planets were forming, and so reduced the eccentricities and inclinations to their present values. Thus, Uranus formed with the other planets soon after the birth of the Sun nearly 4.6 billion years ago. Uranus and its neighbor Neptune, the next planet outward from the Sun, are nearly twins in size. Measured at the level of the atmosphere at which the pressure is 1 bar, equivalent to Earth's sea level pressure. Uranus's equatorial radius of 25,559 kilometers, 15,882 miles, is 3.2% greater than that of Neptune. But Uranus has only 85% the mass of Neptune and thus is significantly less dense. The difference in their bulk densities, 1.285 and 1.64 grams per cubic cm, respectively, reveals a fundamental difference in composition and internal structure. Although Uranus and Neptune are significantly larger than the terrestrial planets, their radii are less than half those of the largest planets, Jupiter and Saturn. For additional orbital and physical data about Uranus, because Uranus's spin axis is not perfectly parallel to the ecliptic, one of its poles is directed above the ecliptic and the other below it. The terms above and below refer to the same sides of the ecliptic as Earth's north and south poles, respectively. According to international convention, The north pole of a planet is defined as the pole that is above the ecliptic, regardless of the direction in which the planet is spinning. In terms of this definition, Uranus spins clockwise or in a retrograde fashion about its north pole, which is opposite to the prograde spin of Earth and most of the other planets. When Voyager 2 flew by Uranus in 1986, the North Pole was in darkness, and the Sun was almost directly overhead at the South Pole. In 42 years, or one-half the Uranian year, the Sun will have moved to a position nearly overhead at the North Pole. The prevailing theory is that the severe tilt arose during the final stages of planetary accretion when bodies comparable in size to the present planets collided in a series of violent events that knocked Uranus on its side. An alternate theory is that a Mars-sized moon, orbiting Uranus in a direction opposite to the planet's spin, eventually crashed into the planet and knocked it on its side. Uranus's rotation period of 17.24 hours was inferred when Voyager 2 detected radio wave emissions with that period coming from charged particles trapped in the planet's magnetic field. Subsequent direct measurements of the field showed that it is tilted at an angle of 58.6 degrees relative to the rotation axis, and that it turns with the same 17.24-hour period. Because the field is thought to be generated in the electrically conducting interior of the planet, the 17.24-hour period is assumed to be that of the interior. The relatively fast rotation causes an oblateness, or flattening of the planet's poles, such that the polar radius is about 2.3% smaller than the equatorial radius. Winds in the atmosphere cause cloud markings on the visible surface to rotate around the planet with periods ranging from 18 hours near the equator to slightly more than 14 hours at higher latitudes. Molecular hydrogen and atomic helium are the two main constituents of the Uranian atmosphere. Hydrogen is detectable from Earth in the spectrum of sunlight scattered by the planet's clouds. The ratio of helium to hydrogen was determined from the refraction, bending, of Voyager 2's radio signal by the atmosphere as the spacecraft passed behind the planet. Helium was found to make up 15% of the total number of hydrogen molecules and helium atoms, a proportion that corresponds to 26% by mass of the total amount of hydrogen and helium. These values are consistent with the values inferred for the Sun and are greater than those inferred for the atmospheres of Jupiter and Saturn. It is assumed that all four giant planets received the same proportions of hydrogen and helium as the Sun during their formation, but that, in the cases of Jupiter and Saturn, some of the helium has settled toward their centers. The processes that cause this settling have been shown in theoretical studies not to operate on less massive planets like Uranus and Neptune. Methane absorbs strongly at near-infrared wavelengths, and it dominates that part of the spectrum of reflected light, even though the number of methane molecules is only 2.3% of the total. Astronomers determined this estimate of methane abundance using Voyager 2's radio signals that probed to atmospheric depths at which the methane-to-hydrogen ratio is likely to be constant. If this constancy is characteristic of the planet as a whole, the carbon-to-hydrogen ratio of Uranus is 24 times that of the Sun. Methane, CH4, comprises 1 atom of carbon and 4 of hydrogen. The large value of the carbon-to-hydrogen ratio suggests that the elements oxygen, nitrogen, and sulfur also are enriched relative to solar values. These elements, however, are tied up in molecules of water, ammonia, and hydrogen sulfide, which are thought to condense into clouds at levels below the part of the atmosphere that can be seen. Earth-based radio observations reveal a curious depletion of ammonia molecules in the atmosphere, perhaps because hydrogen sulfide is more abundant and combines with all the ammonia to form cloud particles of ammonium hydrosulfide. Voyager's ultraviolet spectrometer detected traces of acetylene and ethane in very low abundances. These gases are byproducts of methane, which dissociates when ultraviolet light from the Sun strikes the upper atmosphere. On average, Uranus radiates the same amount of energy as an ideal, perfectly absorbing surface at a temperature of 59.1 kelvins. This radiation temperature is equal to the physical temperature of the atmosphere at a pressure of about 0.4 bars. Temperature decreases with decreasing pressure, i.e., with increasing altitude, throughout this portion of the atmosphere to the 70 millibar level, where it is about 52 K, the coldest temperature in Uranus's atmosphere. From this point upward, the temperature rises again until it reaches 750 K in the exosphere, the top of the atmosphere at a distance of 1.1 Uranian radii from the planetary center, where pressures are on the order of a trillionth of a bar. The cause of the high exospheric temperatures remains to be determined, but it may involve a combination of ultraviolet absorption, electron bombardment, and inability of the gas to radiate at infrared wavelengths. Voyager 2 measured the horizontal variation of atmospheric temperature in two broad altitude ranges, at 6,200 millibars and 501,000 millibars. In both ranges, the pole-to-pole variation was found to be small, less than 1 K, 1.8 degrees Fahrenheit, 1 DGC, despite the fact that one pole was facing the sun at the time of the flyby. This lack of global variation is thought to be related to the efficient horizontal heat transfer and the large heat storage capacity of the deep atmosphere. Although Uranus appears nearly featureless to the eye, extreme contrast-enhanced images from Voyager 2 and more recent observations from Earth reveal faint cloud bands oriented parallel to the equator. The same kind of zonal flow dominates the atmospheric circulation of Jupiter and Saturn, whose rotational axes are much less tilted than Uranus's axis, and thus whose seasonal changes in solar illumination are much different. Apparently, rotation of the planet itself, and not the distribution of absorbed sunlight, controls the cloud patterns. Rotation manifests itself through the Coriolis force, an effect that causes material moving on a rotating planet to appear to be deflected to either the right or the left, depending on the hemisphere, northern or southern, being considered. In terms of cloud patterns, therefore, Uranus looks like a tipped-over version of Jupiter or Saturn. The wind is the motion of the atmosphere relative to the rotating planet. At high latitudes on Uranus, this relative motion is in the direction of the planet's rotation. At equatorial latitudes, the relative motion is in the opposite direction. Uranus is like Earth in this regard. On Earth, these directions are called east and west, respectively, but the more general terms are prograde and retrograde. The winds that exist on Uranus are several times stronger than on Earth. The wind is 200 meters per second, 720 kilometers per hour, prograde at a latitude of 55 degrees S and 110 meters per second, 400 kilometers retrograde at the equator. Neptune's equatorial winds are also retrograde, but those of Jupiter and Saturn are prograde. No satisfactory theory exists to explain these differences. Like the other giant planets, Uranus has a magnetic field that is generated by convection currents in an electrically conducting interior. The dipole field, which resembles the field of a small but intense bar magnet, has a strength of 0.23 Gauss in its equatorial plane at a distance of 1 Uranian equatorial radius from the center. The polarity of the field is oriented in the same direction as Earth's present field, i.e., an ordinary magnetic compass would point toward the counterclockwise rotation pole, which for Earth is the North Pole. The dipole axis is tilted with respect to the planet's rotation axis at an angle of 58.6 degrees, which greatly exceeds that for Earth and Saturn, less than 1 degree. The magnetic center is displaced from the planet's center by 31% of Uranus's radius, nearly 8,000 kilometers. The displacement is mainly along the rotation axis toward the North Pole. The magnetic field is unusual not only because of its tilt and offset, but also because of the relatively large size of its small-scale components. This roughness suggests that the field is generated at shallow depths within the planet, because small-scale components of a field die out rapidly above the electrically conducting region. Thus, the interior of Uranus must become electrically conducting closer to the surface than on Jupiter, Saturn, and Earth. This inference is consistent with what is known about Uranus's internal composition, which must be mostly water, methane, and ammonia in order to match the average density of the planet. Water and ammonia dissociate into positive and negative ions, which are electrically conducting, at relatively low pressures and temperatures. As on Jupiter, Saturn, and Earth, the field is generated by fluid motions in the conducting layers, but on Uranus, the layers are not as deep.